All right, guys, one more day on finding limits algebraically. And we're just going to continue what we did yesterday, add a few things to it. Let's hit it. All right, the first one says finding a limit by canceling out a common factor. All right, so what you notice on this one right here is you can cancel. If you take this function that's in there, the x minus 1, you can factor your denominator into x plus 1, x minus 1, meaning your factors cancel. The x minus 1's cancel. So it means we can just take the limit as x approaches 1 of what we have left, which is just 1 over x plus 1. Now, because that's rational, we're allowed just to plug that. We can do the limit by substitution, direct substitution. So I can plug the 1 in. 1 plus 1 is 2, and the limit is 1/2. That's all there is to it because it was rational. So canceling sometimes makes it a little bit easier. Right, also, simplifying can make your life easier. So I'm going to take the numerator of this function they have given us here and just square, multiply, double square. So 9 plus 6h plus h squared minus 9 over h. I'm going to keep simplifying that. Obviously, the 9's cancel. The 9's cancel. So that gives me h squared plus 6h over h. And now I notice everything has an h. So I can cancel out the h's. I'm still just simplifying here, which gives me just h plus 6. Now, that's a polynomial. And because that's a polynomial, you can use direct substitution again and just, say 0 plus 6, which is 6. So the limit is 6. All right, so let's find a limit by rationalizing. This is going to be a weird one. You got to stay with me here as best you can. Notice it says limit as t approaches 0. Now, we learned in a couple days ago, that if you have a limit of a quotient, you could do limit at the top or limit at the bottom and work it that way. But this time, if I put 0 into the denominator, it's going to be 0, so it would not exist. So what I'm going to try to do is rationalize. This is going to sound weird because we haven't done a whole lot of this. We're going to rationalize the numerator. Okay, so I'm going to take this numerator, the square root. It says the square root of this minus 3. When we rationalize it, we multiply by the conjugate, which would be the square root plus 3. And I got to do the same thing to the denominator, which makes it real fun. I'll do that a little bit too long there. Okay, so my numerator, remember, when you multiply conjugates, you can just do first, last. So if I do that, the first I would get t squared plus 9. And the negative 3 times positive 3 would be negative 9. So that's my numerator. My denominator, I would have t squared on this square root, and also 3 times t squared when I distribute that. Right now, what I have now, I'm looking at it, I'm like, well, I'm seeing a t squared. My numerator is becoming just t squared because those 9's cancel. And my denominator, I probably should have left it like this. I probably should have left the t squared out here. I'm going to rewrite that and do it this way. I'm basically factoring that t squared back out that I actually multiplied already. Sorry about that. And I notice now I can cancel. The t squares are gone. I need to move this up a little bit. Let's see here. And then now I'm looking at this. I'm looking at the limit as t approaches 0 of 1 over the square root of t squared plus 9. Plus 3. Now, I'm looking at, I think I can do the quotient thing now because if I did do direct substitution here, the 0 would not make the denominator 0. All right, so I'm doing the limit. I'm going to do the limit of the numerator. And think about this. If you do it this way, if you do the limit as t approaches 0 of just 1, remember we talked about that the other day, that's just going to equal 1. So when I do the numerator, I just get 1 in my numerator. My denominator, if I separate it and do limit as t approaches 0, that says limit, by the way, of the t squared plus 9 inside the square root plus 3, and do direct substitution there, it would give me the square root of 9 plus 3, which is really 3 plus 3, which is 6. So the limit right there is 1/6. One thing you got to make sure that you remember. Remember. A two-side limit exists. And remember, everything we've seen so far is a two-side limit. If I write this, like x approaches 0, I'm talking about approaches 0 from both sides. Okay, so a two-sided limit exists if and only if both of the one-sided limits exist and are equal. Okay, so both of the one-sided limits, the left and right side, must be both exist and they must be equal, or you can't do a two-sided limit. So I'm going to show you what I'm talking about there. Okay, here's a good example of that. This one says show that the limit, that limit right here of the absolute value of x as x approaches 0 actually does equal 0. Now, one obvious way is you can look at the graph. You remember the graph of absolute values of e. And if you look at what's approaching from the left-hand side, we're getting closer and closer to 0. If you're approaching from the right-hand side, getting closer and closer to 0. So graphically, it looks good. Okay, now, this is going to look kind of weird. This is a piecewise function, but it's actually the absolute value. It says this: the absolute value of x is itself if x is positive. Think about that. The absolute value of any positive number is itself. Now, if x is negative, absolute value of x is the opposite of x if it's negative. That means that if you take the absolute value of -2, you get +2. Okay, so the absolute value sometimes of the number inside is the opposite of that number, and sometimes it's exactly that number. Okay, that's how you'd write the absolute value as a piecewise function, which helps us do this limit here. So what I'm going to do is I'm going to do the limit of each one. I'm going to do the limit of absolute value of x equals, I should do this, as it approaches 0 from the positive side, would be the limit of x as it approaches the positive side, because that's what it equals if it's the positive side, and that does equal 0, just plugging the 0 in. All right, now, if I go the other way, if I go the absolute value of x as x approaches 0 from the negative side, I would get this. I'll get limit of negative x, because that's what it is, from the negative side. Now, again, use direct substitution, plug 0 in there, you get 0. Now, because they're both 0, only because both those limits are 0, the main limit of the whole function is 0, because the left side and the right side were the same. Now, I'm going to show you one next that's not the same. Okay. Just like we did last time, except the opposite, this one says prove that the limit does not exist. So what I'm going to do is I'm going to show that you get a different number from the approaching from the left than you would from the right. All right, so here I go. So I got limit as x approaches 0 of absolute value of x. Let's go to the positive side first, over x. Now, if you're coming from the positive side, as x approaches 0, you would get positive x over x, which is just 1. All right, now, if you went limit of x approaches 0 from the negative side of the same function, obviously the absolute value of x is either x if it's from the positive side, but from the negative side, it's negative x over x, which would be -1. And because those two limits are not the same, that means you get a different limit when you approach from the right-hand side than you do from the left-hand side. The limit does not exist. One more slide. All right, we've got a piecewise one here, and it's asking you, does it exist or not? You know, it's not saying show that it does or does not. You got to show whether it does or does not. So we have to do this, especially with piecewise. We've got to find the limit of each part of it, each function, and show that it's the same whether you approach it from the left or the right. So I'm going to take, first of all, coming from and it does say at 4, so I'm going to approach 4 from the right-hand side, which is this side, by the way. Okay, it's that side, because the positive side is greater than 4. Of x minus 4. And because I'm doing this, because it's a function, because it's a polynomial, I can do direct substitution there. And I can say 4 minus 4, which is 0, and you get 0. Let's go the other way now. The limit as x approaches 4 from the negative side. All right, and if it's the negative side, now I'm using this one because less than 4 is the negative side. So I'm going to do the a minus 2x. Now, remember, the answer will be it does exist, or I can find the limit if it does exist, if they're the same. So again, use direct substitution, plug the 4 in, that'd be 8 minus 8, which is 0. Now, because both of these answers are 0, both limits are 0, I approached it from each side of the 4 and got 0, the limit would be 0. So the answer is 0.
Hey, Mr. See you then.
We'll work on it in class tomorrow.
See you then.